Okay, so welcome to our class today. So chapter 9, we're skipping the previous chapter about aggregation. So this is not going to be tested. You can read it. I think it's useful, but it's kind of an old chapter. So instead, we're going to do discrete choice and random utility. So what is the difference between these and other chapters? First of all, we're going to introduce here a new notion, which is the notion of random utility. But in order to do so, I'm going to start with a simple problem. And this problem is a problem of discrete choice. So there are capital J alternatives. This is a finite number of alternatives. Think, for instance, the problem of buying a used car. Imagine that you want to buy a used car, right? So essentially you have a budget and then you have a set of cars that you can buy. So you go to a used car patio, right? And then, turns out that there are capital J alternatives. So you have 5 possible alternatives that you like, that you are going to choose from. And essentially the problem here is a problem of if you choose one of the cars, then you are not going to buy the others. So you're going to maximize utility with respect to the car that you're going to pick. And there is, of course, the option of buying other things. And these other things are going to be captured in this variable set. Set is the money that you're going to spend on something that is not a used car, okay? What is the price of the used car? Is PJ. So there is no quantity here because you either buy one car or nothing, right? So this is discrete choice in that sense. So PJ is multiplied by 1, which is the quantity of the good you're buying, okay? And of course, this is only the price of the good you actually purchase. So if you buy a Honda, for instance, then you're going to buy with the price of the Honda. If you buy a Toyota, then that's going to be the price of the Toyota there. And then there is, of course, a price of the outside good. Of course, this quantity, if you realize, is just the multiplication PZ times Z. So you can think of this quantity as a single entity. And this single entity is essentially the expenditure on other goods, on the outside option, okay? And this has to equate your budget, which here is denoted by Y. So then the Y is changing a little bit in notation with respect to mass coded because it's not mass coded chapter, right? So this notation is following other sources, right? From discrete choice. So in discrete choice, in general, people use Y as income, but as you can see here, everything is well defined, so we can understand. Do you understand the problem? So here, instead of buying a commodity vector of quantities, you instead buy a discrete alternative, right? And then you spend some money on outside goods, right? And this is the PZ times Z. Okay, so essentially your choice set is set of alternatives and there is an outside option. Everyone understands? Now, here there is some additional things to understand. First of all, essentially, the utility you derive as individual I from alternative J is coming from the set of characteristics of the brand J. For instance, you can have a car that has mileage, gas consumption, price, right? And all of that is, well, price is actually separated here. So price is not in X. Price here is going to be outside, but X contains other things that are features of a car, for instance. And then, we also are going to denote this quantity set as the outside good, right? But not purchasing anything. So if you select J equal to 0, then you don't buy any car, and then you spend everything on the outside good. Okay. Now I can do something simple to make this problem easier to solve. So how do I maximize this? Obviously here, there is no differentiability, right? So I'm gonna substitute set, which is the outside quantity, for yi, which is the income, minus price of set divided by pj. So this is just from solving the budget constraint, right? So I can solve for set. Now, once I do that, I can just replace in the indirect utility. And then I'm gonna get this indirect utility now is a capital U of individual I of item J that depends on the features of J, price of J, price of the outside good, income. And essentially, this is the utility that you observe here above, evaluated and set is equal to this quantity. Okay, so this is just a simplification. I can just replace Z by the quantity that depends on prices and on income. And I'm gonna obtain sort of an indirect utility. Now, what is the utility of the outside good? If you select 0, then you spend everything on the outside good, right? So this is gonna be, of course, you can normalize it because utility here still has a ordinal filling. So this is gonna be equal to 0. So I'm just gonna normalize the utility of the outside to 0. Now, once I have done this, then the problem just is very simple, right? So the consumer ranks every alternative and computes the indirect utility, and then chooses the alternative that gives you the highest utility, right? That's what you do. So essentially in this step, I have removed the budget, okay? So there is no longer a budget here. I'm just solving the problem as maximizing this utility. Any questions here so far? So very simple, right? This is a discrete choice problem. I'm buying a used car. How do I do it? I compute this indirect utility of each used car. I rank them. I choose the highest rank utility level, right? So the one that maximizes this utility. So now, by the result of maximizing is discrete choice, basically individual I will choose J whenever the utility of J is greater than the utility of J prime for all J prime different from J. In other words, you pick the maximum utility item. Now, here is the new part. Okay, so this problem is easy. Now, when you're trying to study this situation, of course, trying to understand why each individual likes a used car in particular, right, is very hard. Also, another issue that we have with discrete choice is that it's very hard to collect data from one individual many times. For instance, in purchasing used cars, how many times does a given individual I can purchase a used car? Not many, right? Usually, for instance, say in a given year, probably you're gonna just buy it one time. And probably it's not even a given year, probably in 5 years, right? Depending, for instance, if you go to grad school, you may buy a used car at the beginning of grad school and keep it, okay, to the end. So that's essentially a discrete choice problem. So in real life, discrete choice problems usually do not happen very often, right? Now, if that's the case, then it's very hard also to try to infer preferences, right? For instance, if you just buy, you go to a patio and you buy essentially a Honda, right? We know somehow you like the Honda better than the others, but do we really know, what particular decision process led you to that? Can we infer your preferences? Well, you don't have really many variations, so it's really hard. Besides saying, Honda is the best for you. So of course, economists would like to know more. In essence, right? Especially in this used cars world. Say, for instance, that someone hires you to try to study, the market structure of brands in the secondary market of cars. So how are you going to study this, right? So essentially, instead of studying just one individual, you'd like to study a population of individuals. So what I mean by that is that a more interesting object and actually a richer data set is just studying the cross-section of all, for instance, grad students or potentially all young adults in London, Ontario, that are in the market trying to buy a used car, right? So when you do that, now essentially you have now a population, in fact, of discrete choice events, okay? Now, when you have that, the problem comes in the following way. So how do I deal with a population of decision makers? So a little bit the object of the study is going to change because we no longer have experiments such as the one we study in the problem set, where we have one individual with 50 experimental trials, right? And we can study each fixed individual given their 50 trials, which is a lot. Instead, we have one individual choosing one time, but we have a collection of individuals. So the object of the study has changed, right? So now instead of having a time series of choices, we have a cross-section of choices, right? So now this is coming from a population of agents, okay? And each agent is choosing one time, okay? So the question comes to our minds of how to even infer preferences in this situation. So a practical guy will do the following. Let's say, look, okay, maybe, in this population, everyone utility is given by a component that is common across all individuals. That means fix utility V that only depends on J, that means on the alternative. And of course, it depends on the attributes of each car, on the price of each car, the price of the outside option that is common to everyone. And of course, you can evaluate it at the income level of each individual. So here in this V value, you're basically capturing the idea there is a common average utility, right? Average, quote unquote, because we haven't defined anything yet. But the idea is that there is a common utility to everyone. But however, we recognize that people differ in tastes for very different reasons. And we cannot possibly capture all those reasons that makes your actual preference differ from one another. So we're going to do something that a lot of social scientists have been doing, that is sticking to this deterministic utility, a stochastic term. So we're going to introduce additively an epsilon ij. So this epsilon ij is really cool because it's a new way to model the behavior. It's going to be essentially a random variable. So a random real variable distributed under some random distribution, right? That is going to change across individuals in a very particular way. This is going to be a random shock that is going to be assumed to be IID. So what is IID from the Niels classes? So it's identically and independently distributed, right? So there is going to be an unknown but given distribution, right? And all of them are all individuals in this population is gonna having draws of this taste shock. So in particular, what this is saying is that the individual utility for alternative J, for individual I, is the summation of a average term that does not change with individual, is deterministic, only changes with alternative, and the stochastic term. And this stochastic term is going to be, of course, changing with individual, but in a stochastic way, being, of course, independently distributed according to some fixed distribution, therefore identically distributed. And there is going to be an epsilon per alternative. So the way shocks affect you is going to change by brand of car. So there's going to be a shock for Honda, there's going to be a shock for Chevrolet, and whatever other brands you want, GM. So do you understand this approach? So essentially, the first idea we're going to introduce here is the idea of random utility. That is essentially saying that at least in this particular first version of random utility, this is claiming that we can model individuals as being as their preferences being the product of a mean utility that is not going to change across individuals, deterministic utility term, plus a stochastic term. And this stochastic term is going to be interpreted as heterogeneity taste, right? So taste is to your shocks to your taste. Okay. So now let's think about it. So a little bit idea of this model is the following: is that you go to try to buy a car, and you like Honda. You like Honda because it's a good brand, right? So there is an X describing that Honda is a good brand. So the reputation of the brand. Then there is a mileage. So you say, okay, this car hasn't been, around much. Probably someone was commuting to a very near place or has low mileage. It doesn't consume much gas. That's a plus, right? It has a color that you like, okay? Maybe it has automatic transmission versus manual transmission. So some of us, come from countries that they use only manual transmission, right? So we learn to drive like that. So something that's a plus, right? And so on, right? There are so many features, and all of those, right, enter into X. Okay, great. So now the idea is that somehow if people use that, run them in some common way. And then, you say, look, this car, I actually like it because it reminds me of a car that a friend had, and we had a really great time with this, right? So they say, okay, this is a fun car. So what is that, right? Another reason is you say, oh, look, this car has a funny sticker, and I really like it, maybe it has good vibes or whatever. This other car, just has a component that the seller, comes and really, talks wonders about the car and tells you, no, buy Honda. Honda is the best. You cannot go wrong with Honda. This is your lucky day. This car was driven by someone that doesn't even like to drive, so this person never take it out. So there is this random component, right? That decision, specialists, empirics, or theories cannot really fathom and actually understand the complexity of why you particularly like the Honda versus the Toyota, right? And sometimes, choice is a mystery. So this is a little bit what we're trying to capture with this mysterious epsilon ij. So it's a shock, right, to utility that we cannot really exactly pinpoint or predict for each individual, but somehow we can try to describe as a population level, okay? So I'm gonna make here a claim. So a little bit here, the idea is that instead of trying to predict exactly what each of you is going to choose, right? We instead are going to try to describe the population behavior. So when we introduce this epsilon, we give up on individual prediction, right? So we give up on individual prediction. I'm not going to be trying to predict exactly what any of you will try to basically predict, right? This is not possible. This is not possible. So instead, by adding this epsilon, I'm gonna try to focus on a population quantity. I'm gonna try to focus on trying to predict the shares of the population. So the fraction of the population that is gonna pick alternative J. So with epsilon, the thing that I'm trying to model is not individual choice, the choice of Victor. I'm going to try to model the choice of the population of, Yokandols in London, Ontario, going after a used car. And I'm going to try to predict the share of people that buy Honda versus the share that buy GM. Do you understand? So by introducing epsilon, I give up on individual prediction, but I'm going to try to predict population behavior, right? Which in the end is going to be the share of individuals that pick something. So this is a different objective from the previous chapter, right? From the Mascolet chapter, we're trying to predict exactly what each individual decides, chooses, right? But right now we're giving up on that. And now we're introducing this notion of population of choices. And then now we're giving up of the individual prediction of choices. And we just want to predict the share of people buying something, okay? So let me introduce to you this object, which is mathematically a probability of choice, right? And at this stage, right, this is going to be, we're going to be very careful about the notation. At this stage, at this level of generality, I'm not going to force the shocks to be IID, right? So in the most general world, we could theoretically, right, predict the probability of choice of any given individual. And this would be given by this object, which is equal to the probability that the epsilons from each individual I, from alternative 0 to alternative capital J, are such that the random utility, right, of individual I for alternative J is greater than the random utility of individual I for alternative J prime for all J prime different from J. So as you can see, this is measuring, right, the event inside the probability. There is an event. The event is that the J alternative is the top, right, is the most preferred item and hence chosen. Now, because this happens with respect to the realization of the epsilons, this is measuring the probability of such event, right, given the distribution of epsilon. Do you understand? Okay. Now, of course, this object is almost impossible to obtain, right? Because it will require me to observe an individual choosing almost too many times, right, to be able to compute these probabilities. As you know, many things like choice of cars do not happen very often, right? So in order to be able to have something more useful, people introduced the assumption that the random shocks to taste are IID, so identically and individually distributed, okay? Do you understand? So now, once you do that, and given some fixed distribution, but unknown to the observer, F, now we can compute instead the share of J. So this is the share of people in the population, the fraction of people in the population that buy Honda. And this is, of course, depends on the prices from 1 to J. So from all alternatives, including Honda, from the price of the outside good and the income, right? And this is equal to the probability of the event that the indirect utility Vj, the mean utility minus the indirect utility of Vj prime, is greater than or equal to the difference between epsilon j minus epsilon j prime, right? And this is the probability of this event. So in other words, if you rearrange terms, this is the fact that the random utility of j is greater than the random utility of j prime for all j prime different from j, right? And this is just rewritten such that all the deterministic terms are in the left-hand side and the random terms are in the right-hand side, okay? That's it. And now I'm measuring the probability of this event. And of course, this is given a distribution F. Do you understand? What is different here? The only difference is that now the epsilon is assumed to be distributed identically and independently from this distribution F that I still haven't fixed. And once, if I know the probability, I can compute this share, okay? So now let's...
Can I ask you a question? There is something I don't understand. So what is necessary to... So the market share of J is the probability that the indirect utility of J is greater than the one of J prime, right?
For all J prime. So it's
for all J prime.
Yeah.
So I don't get why do you need to include a stochastic term in order to claim that? For example, if we had no stochastic term, I think we could write a similar definition, right? That the or not.
So right now we're introducing the probability. So because we are assuming that individuals are such that their utilities is the summation of a deterministic term plus a stochastic term. So this is just a modeling technique. So what you're saying is that we can.
Yeah, my question was what is the purpose exactly of adding the stochastic term in the indirect utility function?
Yeah, for sure. So there are two purposes. Well, that's a great question. So let me go a little bit more to the motivation. So the first thing I was saying, right, is that because we don't have repeated choices from one individual, as we were assuming in the previous chapters, right? We just have one choice of one individual. So in order to learn from choices in the cross-section, something about the preferences of these agents, we have to assume that there is more structure to their heterogeneity, right? If heterogeneity is completely unrestricted, so everyone has their own utility and there is no feature or no common structure, then you cannot learn much, right? Because you just have an isolated event from one individual, right? And you cannot learn anything about it. So what we're assuming is that preferences are somehow connected, right? That they have a common structure. So we're assuming that there is a common term, this capital Vj, that is common across all individuals. Of course, conditional on attributes, conditional on prices and so on, and conditional on income. And then, you know, we assume that people differ and they are heterogeneous, but they are not heterogeneous in arbitrary ways. In this particular model I'm introducing, they are heterogeneous because there is an additive term that is identically and independently distributed, this epsilon ij, okay? And this produces a model, right? That is a very special structure model of heterogeneity, where heterogeneity is controlled and restricted. So it's kind of a parametric model, right? So it's analogous to taking the utility in the first chapter and making it Cobb-Douglas, right? So here we're putting restrictions on the fully heterogeneous utility to be able to do something, right? And the reason we do it is because now we will be able to use the cross-section of choices, right? To be able to infer something about the distribution of the epsilon, right? And of course, of the mean utility V. So if we're able to learn from the cross-section of choices, something about B and something about the epsilon, then you can predict what this population of decision makers will do in terms of shares. So for instance, what you are in the end aiming to do is the following. So imagine that you're hired, by someone that is owning several used car patios, right? And they want to know what will happen if, for instance, you change the price of Honda by 10% below. Will this, really increase the profits, or will this just, subtract or substitute from other goods that you actually have a higher margin to the Honda, in the end, making your profits lower? So this is a question that is the classical question, right? A counterfactual question. If you change the price, what will be the change in the choices of individuals? Now, instead of trying to basically predict what Victor will do, you will try to predict what the share of individuals in London, Ontario, for instance, will do if I change the price of Honda, right, by 10%. Okay.
Okay.
So the final, yeah, but that's
super
a great
good question. A super good question. So the deterministic part of the conditional indirect utility is common across all individuals because of simplicity of the model, right? Because it could be heterogeneous as well. Okay.
Yeah, and that's exactly right, Martin. So this first model is super simple in the sense that the common utility is homogeneous, right, which is super strong. And then all the heterogeneity enters additively, right? And of course, this is a first model and it's super, super simple. And then, of course, we can extend it later on. But right now, that's going to be it, right? So it's a great observation. It's a very strong assumption, right? The fact that this common utility is not changing, right? In any way with individuals. Great question. Okay.
Professor.
Yep.
BLP is an extension of this model, then.
Yeah. Okay. So BLP, this is a model from Mayo, right? Is basically the three initials of the three guys that invented it, right? Berison, Levins, and Pax, right? And so these guys, invented a model of discrete choice that is very complete. So it has way more sources of heterogeneity. Okay. So this is a very special version. Okay. Now, so important thing. So how do I observe this data, right? So usually, I observe this data from finite samples of frequencies of choice. So that means I go to today to London, and then I collect data on purchases, right? So I see what is the fraction of people in London, right? Define my population and how many of them, right? This is capital K, the number of people that is my target population. And then I'm gonna compute the choices of these people, right? Of Honda, and then divide this counting divided by the total number of the population. So this is a relative frequency of choice. So if 20% of the individuals that I'm studying chose Honda, now this p hat is going to be 20. Why it has a hat on it? Because we're assuming, as usual, from a statistical point of view, that the population is an infinite number, right? And then of course we're going to get the London and the events of choices that we have in a given year. It's just going to be a sample of it. Now, of course, this object usually is taken as a sample, and so hence you're going to have in reality a p hat, which is a relative frequency, and the classical Kolmogorov argument that if you take k going to infinity and these are IV experiments, then the relative frequency of choice is going to converge to the true probability of choice. Now, of course, it will be ideal if I have an individual choosing many times, and then I can compute the probability of choice of each individual. But that's usually very hard to do, as I mentioned before. So instead, what we do is we take the share of a given cross-section of people. And in that case, I just average across the number of individuals in a given population. So yet again, in theory, our theory should go either for individual probabilities, which means that, for instance, you're choosing in an experiment, hundreds of times, which is very hard to get. And then the other, which is the object that I want you to think more about, which is the share of population, right? And these objects, as the population grows, will converge to the true share. Now, all our analysis here, because we're focusing more on the behavioral part, is going to be done as if we already estimated a perfect estimate of S, or the probability. So for us, the share or the probability is going to be the true probability of the true share. So we're not going to mess with the sample variability, and we're not going to mess with the statistical testing. Right now, the only thing we're going to do is studying what happens if I have access to the true share or the true probability. How can I recover information about preferences, right? So as you can see, this is the same question as revealed preference, but now from a more modern perspective, right? So from this population of people, a share of choices, how can I recover something about the distribution of preference? Now, one important thing before going on. So another interpretation of the random utility is the following: is essentially that no individual has a fixed utility. So this is an individual interpretation of random utility. But instead, your own choices are not stable. So remember what is the main assumption in the previous chapters. So if you remember, one of the key axioms that we studied was the weak axiom of revealed preference. And what was the implication of the weak axiom? It was that if you chose X over Y, then in another situation where X and Y are still available to you, you will not flip your choices. What that can be translated as your preferences being required to be stable, right? So they never change across different choices situations. But I'm going to ask you something very simple. So right now, now it's easier a little bit with the quarantine and lockdown easements, right? So we are a little bit semi back to normal. So you can go to a restaurant, right? In fact, there is this community center mall in Western, and there is some places you can buy food, right? So someday you go and you buy Subway over Tim Hortons, right? You buy a sandwich in Subway versus the Tim Horton one. So you chose Subway sandwich versus Tim Horton, right? So that's X over Y. But then, you go tomorrow, and then you're craving for Tim Hortons. So now you choose Tim Hortons over Subway. So now you choose the Y over X. So that's clearly a violation of word. Now, in both cases, you were maximizing what you like, right? So you were maximizing utility. But what happened? So I mentioned this word, craving. What is a craving? So it's very hard to describe, right? So if you're, maybe you're a neuroscientist, they know exactly that there is a hormone that changes your brain, whatever. But in general, I'm an economist. I don't want to focus on the exact details of the brain functioning. I want a model that is, I can actually make predictions. See, for instance, I'm hired by the guys in Western to be able to see what will happen if you change the price of Subway and how this would change the patterns of consumption and substitution between Subway and Tim Hortons, right? So that's the typical world of an economist. So how do we model all these complexities, like for instance, cravings? Another reason, is for instance that you were trying to go to eat something, and then you receive a message in your phone, right, saying buy Tim Hortons, there is a discount today, or buy Subway, it's healthy for you, an advertisement, and that changes your mind a little bit, right? And then you go there. So all of these things are very hard to capture, and all of them will create violations of the weak axiom. So a key thing that I think we should modernly accept is that the classical utility maximization framework is too limiting, because humans by nature are very non-stable, right? And and essentially, you will change your ideas about most things every day. So if we're assuming utility remains unchanged and super stable, we will probably fail predicting behavior. Now, random utility enters like an alternative to model that. And essentially, random utility assumes that individuals are endowed, instead with one utility, they're endowed with a distribution of utilities, right? And then, of course, if the distribution is completely arbitrary, then everything goes, and then you cannot do anything. You cannot do predictions. So you start putting some discipline on the distribution of preferences, right? And the way to do it, yet again, is assume, for instance, that if an individual is choosing food in the community-centered mall, then you have sufficient number of choices of an individual, and across all choices, even if your utility is random, it is still controlled by a fixed probability distribution. So the probability distribution is not changing every time. So in this way, we kind of recover the idea of the weak axiom, but instead of having the requirement that your choices should not flip, you just require that the probability of your choices should have some sort of regularity, right? And it shouldn't change much. And the probability should have some properties that will remain stable. And in particular, the distribution of preferences should not change. So your preference can be changing, but the distribution governing your preferences cannot change with menus, okay? I know I said a lot. Now these things are very complex, but luckily we have a whole chapter to study this. But what I'm just saying is that there are two interpretations of random utility. The first one that I just explained to Martin, thanks to his question, right, is the idea that you're just thinking of a population of agents, each agent chooses one time, and then you want to learn something about the preferences. You start structuring preferences, and then you assume that each individual has a random utility, but it comes from a common distribution, right? This is the cross-section interpretation. And then there is other individual interpretation of random utility, where each individual actually changes utility. But across many repetitions of your choices, there is still a common and stable distribution of preferences. However, your preferences themselves are not stable anymore. They change because they are random, okay? And this is the modern notion of individual random utility, okay? Both things are compatible. And in fact, for instance, you can have a population of individuals, each of them being random utility. And turns out that the aggregate behavior of individuals that, such as those that I described, is still random utility, okay? So it turns out that a random utility admits both interpretations, either the individual random utility one or the cross-sectional population one, okay? So once we have done this, we're going to introduce the first model, which is the very easy, historically important model of stochastic choice. And this is called the multinomial logic, okay? You can think of the multinomial logic as being the analogous of the Cobb-Douglas for the previous chapter, right? So it's a parametric restriction on random utility, okay? And the parametric restrictions enters in terms of the distribution of the shocks of this additive random utility model. So we're going to assume this is a distribution called a type 1 extreme value. And essentially, this is a double exponential distribution where you have two parameters, the eta and the mu, right? And in particular, we're just going to play with this eta. We're going to fix it to something called the Euler constant. And then we're going to fix the scale parameter to 1. So the two parameters are fixed. And once you have fixed them, essentially, we can compute this probability of choice according to this distribution, the type 1 extreme value. And once I do it, it turns out that this will give you a closed form solution, okay? And the probability of choice of J is going to be equal to the mean utility, right? So let's change a little bit this. Right now it's a bit confusing. So the mean utility, which is exactly, does not depend on I, right? And in this case, right, this probability of choice, right, is going to be equal to the exponential of the mean utility divided by the sum of the exponential of the mean utility of all other alternatives present in the choice. In this particular case, from J prime equal to 0 to ... capital J. So what this is saying, this is very cool, right? It's saying that the probability of choice of alternative J is proportional to the exponential to the mean utility. So in other words, is proportional to the mean utility of the particular good. So if you compute the mean utility, you can then know exactly what is the probability of choice, right? And y is divided by the sum is essentially just a normalization, such that this probability adds up to 1, okay? So if I add these probabilities across all J, it will add up to 1. So it's a well-formed probability. So again, this is a very cool model because it is giving you a closed form solution of this complex integral. And this integral is essentially integrating over the area of the epsilons such that they satisfy that J is the top alternative, right? Over the distribution F, which is given by this type 1 extreme value. So if you do it this by hand or using Mathematica, you're going to obtain the probability of choice of logit. Okay. So this model, again, is really cool. It's very tractable. People use it until today. You know, if you go in state discrete choice modeling, people still do logit, right? And logit, you know, the main reason people do it is because it's one of the models that is so tractable and nice that people could do it before the age of big computing, right? So remember that one of the issues of random utility was that you have to compute actually this integral. And compute this integral, you know, depends on how hard is compute this integral depends on f. So if f is a super complex distribution, right? And remember, this distribution is over a huge random vector. So the random vector here, you know, potentially is epsilon that goes across all goods. So for instance, imagine how many cars there are in London, Ontario. So used cars, you know, even if we think only in brands, possibly above the 20, right? So it can be a huge vector with 20 entries, right? So now you have a distribution over 20 things. So of course, you know, one way to do it is here is assuming that f of epsilon assumes that every good across either Honda, GM, follows the same distribution, right? So it's the same f. And then I integrate across all of that, and then I get this very nice probability. Okay. Now, this is not the only model possible. If I take, for instance, that the distribution of this difference of epsilons follows a normal distribution, then I obtain a different model called the Probit model. Okay. So in fact, depending on the distribution f, I obtain different models of choice. Okay. Now, one important thing about the Probit models is that, as you can imagine, you can introduce a multinomial normal with correlations across epsilons, right? So I can model that the shocks are correlated across goods. So it's sometimes a more flexible model. But before going to this Probit and other models, so in general, you know, there is a whole industry about people replacing F with different specifications to capture different phenomena. We're going to study the implications of logit. And we're going to do it in order to understand what's going on with logit, right? So yet again, as you remember, this is analogous to a Cobb-Douglas, so to the spectral utility is a parametric restriction of random utility. So now, one key questions we have been asking so far in this class is what are the empirical implications of multinomial utility, right? So the most important implications is the independence of irrelevant alternatives. So yet again, another name that has independence. Don't be fooled by this name. This is not the same as spectral utility, right? This, in fact, is the independence or irrelevant alternatives, IIA. And this just tells you that when you're logit, the following condition will hold. So if I take the probability of choice of alternative J, and then I divide it by the probability of choice of alternative K, this is equal, and let me make it bigger, to the probability of choice of J divided by the probability of choice of K for a different menu J prime. So essentially what this is doing is saying, look, take a menu J prime, which is basically a different menu from capital J. So imagine instead of London, you go to Waterloo, and then Waterloo, there are more alternatives of used cars, right? So now the menu has changed, right? The menu has expanded. So J prime is a bigger menu than J. Then if that's the case, if you take the probability of choice of Honda versus GM, for instance, and the probability of choice of Honda versus GM in Waterloo versus the probability of Honda versus GM in London, Ontario, it has to be that these odds or these ratios of probabilities are the same, irrespective of other alternatives that may be there. So in Waterloo, there are more alternatives than Honda and GM, right? So, but even if these alternatives are there, they turn out to be irrelevant, right? So that means that the probability of choice or the substitution pattern between J and J prime and K, sorry, is independent from any other alternatives you have, right? So it remains constant. Now, the first thing we're going to do is verify that multinomial logit implies this probability. And this is very easy to check because if I take the ratio of the probability J divided by K, it's essentially exponential of the mean utility J divided by the exponential of the mean utility K. Do you understand? So if IIA essentially is the benchmark or the defining feature of the logit model, okay? But that's why we like to derive these properties. Yeah, go Martin.
No, it's okay.
Yeah. So now, why do we do this? So remember that we derive the testable implications of models because we want to know if the model we're using is sensible or not. Remember logit, we use it because it's tractable, right? Because back in the time, people didn't like to use computers to integrate. Maybe they didn't have a good computer, right? So they had to do it by hand. So they chose out of convenience, right? The distribution of logit. But they didn't choose it because empirics or laboratory experiments tell you that it's a good distribution, right? They didn't do that, right? It's not like physics. They did it because it was mathematically convenient. Do you understand? Now, if we do that, we know that tractability has a cost, has a price to pay. So in order to understand the price we're paying in terms of the capacity of this model to be able to explain real behavior, is we derive the testable implications of this model, right? So by deriving the testable implications of this model, we obtain the IIA condition. Okay, great. Everyone understands it. And now it turns out that this IIA condition may be actually not a great model. And this was introduced by Debreu, similar to the Allais paradox. Debreu produced this Simly paradox. Again, it's not a paradox, it's not an experiment. It's just a thought experiment of Debreu that pointed out that IIA may not be a great model after all, okay? And this is called the red bus versus blue bus problem. Historical note, Debreu was more educated, so he produced the original example using classical composers, okay? But of course, now after this has become more popularized, and especially in some books like the Trains book in discrete choice modeling, they have changed it to the more popular red bus versus blue bus, right? So for us, the common people. So now with this in hand, you know, let's go and let's understand what's happening. So say you have two options. So W for walking and RD for taking the red bus. Now assume that the probabilities or shares of choices is the probability of walking when these two options are the only ones in town is 50%. And the probability of taking the red bus is 50%. That means out of the population of London, for instance, 50% of people are gonna walk, 50% of people are gonna take the red bus. What is the odds ratio of this? Ratio of this is 1, okay? Now the City Transportation Corporation introduces a new bus, which is called the blue bus, that is identical to the red bus in all attributes except for color. It is blue. In fact, it's a nearly perfect substitute while not being a substitute for walking, of course. Now, given this, what should you expect in terms of substitution patterns, right? So if in fact, you know, this blue bus is the same as the red bus, except that it's blue. Now, you will expect that the people that were taking the bus, right? They, of course, randomize between red bus and blue bus. So you will expect that the probability of the share of people taking the blue bus is around 25%, right? And the blue bus is, of course, 25%. And of course, walking should be left alone, because the introduction of the blue bus is not changing anything. Here, of course, this is assuming that there is no capacity constraints, right? It's like city in London where things are half full most of the time. And now the odds ratio here, of course, is gonna be that the probability of walking versus red bus is equal to 2, okay? But here, red flag, right? What's happening? So the odds ratio of walking versus red bus in the original menu is equal to 1. And now the probability of walking versus red bus in the menu with 3 alternatives, one of them a duplicate, is equal to 2. So that fails the IIA, right? That fails the IIA because IIA requires that the probability of walking versus red bus is still 1, okay? So this is, of course, it seems to be something sensible, right? So this is not data. This is not a logical paradox. It's just a thought experiment. And the thought experiment is telling me, look, it is reasonable to think that if I introduce a duplicate, a blue bus, it shouldn't take away the share from working, right? It only should take away the share from the red bus. But if I just follow, a common sense, and I think that in fact red bus and blue bus are duplicates, then people should be indifferent between the two of them. So, natural prediction in this case is that people randomize with flipping a coin between red bus and blue bus. So they will be 25%, 25%. If I do that and working is left alone, IAA is violated. Okay. So do you understand what is the issue? The issue is, of course, that this nice assumption of the type 1 extreme value distribution of the shocks is very restrictive, and you're paying a price. The price is that the substitution patterns are too restrictive, and then it would rule out something like this that sounds very reasonable, right? So this very reasonable story fails the IAA. Now, yet again, we're more modern than these guys. So we should really ask the question. So in experimental data, in real data, does the IAA usually is violated or not? Remember that the IAA is the testable implication of the multinomial logic. So you can never see the actual taste distribution, right? You cannot see the distribution of shocks. So you cannot see whether the distribution of shocks is logit or not. That's impossible, right? We derive the testable implication, which is the IAA, and that thing is testable. So you can go to real data, compute the shares, and then compute whether or not the IAA holds. So people have done it, of course, and then IAA usually fails, right? So IAA is not a great assumption, it's too restrictive. Now, that doesn't stop people from still using logit, right? And the reason is that logit is so nice and simple, and if you put it in data, right? Logit, whatever, is gonna converge quickly, right? Because it's a very well-behaved model, right? So people are gonna use it, and because it's simple, not because it's good. And remember, right, that the reason is not recommended to use it is that it implies this IAA condition, which is very restrictive, right? Super restrictive. And of course, this simple example illustrates that. Any questions here about the red bus, blue bus? No, right? But again, one thing I want you to realize is that that's the objective of this class, right? So we take some model of behavior, we understand why people did it, how it works, what is the model, and then we essentially derive testable conditions, right? And the reason to do it is because with testable conditions, then we can decide whether the model is good or not, right? So using IAA here, we understand that logic is not that great, right? So it's problematic. Now, let's be a little bit more formal about logit, right? And here, you're gonna see from my notes, right, that I switched to this loose model. So the reason I did it is because historically, the logit model is the name people use in economics, but the model was originally created by a psychologist, and the last name of this psychologist was Luce, L-U-C-E. So Luce invented this model by observing some data in his laboratory, saying that people, basically, the probability of choosing something from individual stochastic data was proportional to the impulse. So he was giving impulse to people by showing them some neural stimulus, for instance, some particular screen, some color, some price, and then he observed that the probability of choosing the object was proportional to the intensity of the stimulus. Of course, that may be in some cases, right? But in many cases, the Luce model fails. And in particular, in economics in general, that is not a great model. However, it was adopted, by McFadden, that he won the Nobel Prize because of this contribution in a stochastic choice, because it was very nice and tractable, right? McFadden, when he introduced this, he didn't have access to great computers. Essentially, eventually, as he was progressing his research of random choice, computers were also improving, and he was able to generalize a lot of his early work. But the original work that he was doing was basically the logit model, which was the name he gave it to this model, but originally was the Luce model. So a lot of decision theories still use the loose name, right? And now let X be the finite choice set, right? And to use the notation in our previous chapter, now introduce a collection of menus. Menus are, of course, equal here to the power set minus the empty set. Now take a menu A and define the following object. So who recognizes the symbol? This is a simplex, right? So the simplex is the collection of probabilities over A. So now we take a menu and we put a probability over that menu. And this object is going to be called row sub A. And this is describing the probability of choosing alternative A inside menu capital A, okay? So this is a full description of the probabilities of choice, okay? So remember, this is now our object of interest. Now we go back to the environment of the first chapters where we allow menu variation, right? And remember that row is such that adding up over alternatives equal to 1, and each of them is a positive probability. Now define the collection of all such probabilities over each menu. So remember that each menu has a probability of choice inside it. And then I take the collection over all menus, right? And then I put it inside a row without sub A. Everyone understands the object I'm creating? So this is just an experiment, right? Where I have a population of agents. Randomly, a fraction of population of agents is assigned a menu. Inside this menu, I compute the probability of choice of each alternative inside the menu, and then I move to the second menu, and then I compute again the probability of choice of each alternative inside the second menu. Then I go to a third menu and so on. All of this information is collected in this row. Everyone understands this? Okay, so this is a collection of probabilities of choice, and then I'm basically collecting across menus. Do you agree? Okay, so in the previous example, we have the menu Waterloo and London, right? Of used cars. Now here we can allow much more menus. Okay, so in this framework is completely general. So now if I have this, I call a complete domain if we have all menus, and then in that case we can also call this a stochastic choice function, right? Now what is loose IIA is for any menu A and B, and for any alternative A and B that belong to the intersection of A and B, then the probability of A over the probability of B in menu A is equal to the probability of A and the probability of B when I'm thinking of menu B. So when the probabilities are positive, this is loose, okay? So it's exactly the same condition I described before when I have London and Waterloo, but this is more general. Now, what is the theorem? This is a characterization theorem. The following are equivalent. Rho satisfies the loose IIA, and rho admits a logit representation. So logit or loose representation, right? Depending on the name. So let's prove 1 implies 2. So for all x, basically we define Wx is equal to the exponential of b of x, which is equal to rho x for the alternative x. So essentially I fix the grand menu x. I take alternative small x, and then I equate this exponential of bx equal to this value. Okay, so this is my definition, is a candidate mean utility. Okay, and this candidate mean utility, I put it inside exponential, nothing more. Okay, now once I do it, right, then we have to verify that it generates rho for all other menus. So this is the candidate mean utility. I want to check whether this candidate mean utility generates the data for all other menus. How do I do it? Well, fix a menu A different from X and fix an alternative X prime in A. So this is a fixed alternative, like Honda. Now by IIA, I notice the following. So notice that IIA tells me that the probability of X in the menu A divided by the probability of X in X is equal to the probability of A, right? Probability of A divided by the probability of A of X star is equal to the probability of X in this grand menu X divided by the probability of X star in X. So remember, this is IIA. So just let me rearrange it such that we understand exactly what's going on. So there is no confusion, right? So this is IIA. This is IIA. And now the only thing I'm changing is the menu. So instead of having the menu A, I'm gonna change it to menu X. Okay, great. So now this is IA. Now rearranging terms with positive probability, I get the probability of A of X is equal to the probability of X small x times probability of A X prime X star divided by probability of X star. So now notice that these terms here, right? These two terms here with the X are just the WX and WX star by definition, right? So remember that in the grand set X, I equated this to the WX, which is the exponential of the mean utility. Do you agree? So I make this substitution and then I obtain this probability of A X star. But now I take this quantity and I add up over all alternatives in the capital menu A. So I take this and add up over all alternatives in menu. So changing notation slightly. So summation over the probability of A of Y over Y in A is equal to the summation of WY probability of A X star WX. Note that X star is a constant, right? Because the summation is taken over Y. So I can take this outside. And now it turns out that it tells me that probability of A of X star is equal to, when solving for this, is equal to the exponential of Bx, which is the Wx, divided by the summation over the exponential of dw. So after adding up, I essentially take the part that doesn't change with y out of the summation. This ratio, now I can solve for the probability of I X star, and then essentially it gives me the probability of X star in terms of the Wx. And then I can, of course, generalize it and write the formula that probability of A of X is equal to the exponential of Dx, which is Wx, divided by the summation of Wx, which is essentially exponential of Dw. Okay, so any question here? So this is a super simple proof because it takes this mean utility is just equal to the probability, right? So that's the only trick. Once you have obtained it by IIA, you can use that mean utility to generate the rest of the data. Okay, so now we have characterized the model. IIA is not only an empirical application, it's also the sufficient condition. So this is the analogous of the GARP for the rationality, right? But for the world of stochastic choice, the Luce or the logit model is equivalent to IIA. Okay, understood? So if IIA is violated, then Luce is dead, right? Luce logit. Okay, so we have an hour, and now it's time to increase the level. So right now I introduce logit. Logit is a nice model. It's a cute model, but it's very simple. So we have to do something. And the question is, how much general can we go without losing empirical value, right? And this is essentially the theory I'm going to introduce. So this is the random utility theory in full generality. So this is, as you can imagine, this is the non-parametric analogous. So this is the non-parametric utility analogous of the world of GARP, right? As the logit was analogous to the Cobb-Douglas, right? The part that we're going to study here is the analogous to the Afriyat's theorem. So it's the fully general non-parametric random utility. Okay, so this is very general. Okay, so now take a choice set X and consider, now we're going to introduce this, a probability space. Okay, so this is where the people that are paying attention in IELTS class are going to be happy, right? We have a probability space, which is a universe of events, omega, sigma algebra denoted by calligraphic F, and a probability measure, right? And we're going to have that this is a F measurable random utility function. So utility is actually here a random object, right? Mapping from the set of events to the collection of utilities. So important here. This is not, I was careful of not saying U is a random variable, right? I say U was a random object, okay? In fact, the image of this function are functions themselves, right? So this, in fact, is a measurable function mapping from events to utilities, utility functions, okay? So I'm going to explain with an example so you understand. So an example of this object is a random Cobb-Douglas utility function. Look at the random Cobb-Douglas. So this is a utility function. So a realization of this random object is u of xy is equal to x to the alpha, y to the 1 minus alpha. And then alpha is a uniform distribution in the 0, 1. In this case, omega is the set of events from 0 to 1. Do you understand? So essentially, for any realization of omega, right, of this alpha, then there is a utility function. Do you understand? So each realization is a utility function itself. Okay? Do you understand what's going on? So here, a random utility, remember, is that if you fix an event in the space omega, it gives you a utility function. Okay? Random variables, as you studied with Nail, is that you fix an event and it gives you a real number, right? So random variables or random vectors essentially have realizations, random real values or real vectors, right? This is what people study in econometrics. Here, we have something more general. Once you fix an event, you have a utility function, right? So it's a whole function, okay? So changing the event changes the function. Example, the random Cobb-Douglas, right? As you change alpha, right, it gives you a different Cobb-Douglas with a different share, okay? Now, let's define a choice event. So C of X of A is the event in which the agent chooses X from menu A. So essentially, this is the collection of omegas in capital Omega, such that the realization of the utility, right? So U of omega of X is strictly greater than U of omega of Y for all V in A minus X. Do you understand? So essentially, because each omega defines a utility function, defines a preference, right? Then this event is telling you that this is this collection of omegas where X is better than Y, okay? X is the best alternative possible. Now, important thing, how do you interpret this, guys? So in the random Cobb-Douglas. So essentially, you know, this is about talking about now a different kind of heterogeneity, right? Before we talk about additive heterogeneity, we tested shock centers through epsilon, right? So epsilon was shocking the mean utility. Here instead is a way more general way of introducing random utility. For instance, in the Cobb-Douglas, heterogeneity comes in taste, right? So you know alpha controls the taste between goods X and Y, right? So the higher the alpha, the more you like X versus Y. Essentially, as alpha goes to 1, you only like X and you discard Y, right? So now, yeah.
Yeah, Victor, could I ask you, like, apart from the example that we are studying right now, what is exactly an event in this context? Because I'm thinking of, for example, a menu is an event.
Yeah. So here is very interesting. So these events can be actually anything. So it's so general that these events can be ranging from variation in taste. It can be, for instance, also variation in risk aversion, variation in delay in time. It can be attitudes towards uncertainty. It can be mistakes. It can be anything. So these events at this stage are super abstract and they just capture any source of hidden heterogeneity that we cannot capture as decision theories. So this is a factor, right, that has some probability and captures things such as cravings, attitudes towards risk, taste, you know, things that the decision maker cannot possibly capture all at once for any individual. So Omega aims to capture with full generality all of these things, right?
Okay, so they are contingencies on preferences, but not on alternatives.
Yes, so these
Okay,
are only hidden states, if you want, of preferences. So one way to understand it is, for instance, the word moods. So remember the example that I gave you about buying in restaurants in Western. So for instance, when you chose Subway versus Tim Horton, maybe you were in the mood of trying to be healthy, right? So you were trying to get, healthier meal. And then when you chose Tim Hortons over Subway, maybe you were in the mood of being saving money, right? So you're saving money. So you put a little bit more emphasis on that. So in that particular case, for instance, Omega can be thought as moods. Another way to interpret Omega is, for instance, hidden states of the world. For instance, I am an observer, and then I only see choices from you from the community center, right? And then I saw that one day you bought a sandwich with a with a warm drink, right? And the other day you bought it with a cold drink. Now that means you violated against word, right? Because one day you chose cold over hot, and the other day you chose the opposite. But then, possibly not in the data set of the decision empirist was the information that one day was very cool and the other day was very hot, right? And that information is captured in omega. That is a hidden state of the world, right? So versus why some people, chose a Honda a particular day, maybe because it was a yellow car and it was a very sunny day. You feel summery, right? So that's something that you cannot possibly capture in terms of prediction, right? All of that is hidden in omega, okay? So it can be hidden moods, hidden states of the world, right? Variation in taste. It can also be heterogeneity. So variation in taste, variation in risk aversion. So omega tries to capture all of that. And then the only thing we're assuming is that for each omega, there is a utility, okay? And that's the key assumption, right? And on top, of course, we're gonna assume that there is a unique distribution that controls this, right? And is stable across menus. So this doesn't change with menus, okay?
So among all the things that you mentioned that are included in omega, awareness of the different alternatives that are available is one of the contingencies, right? Okay.
Okay, that's a really great question. So awareness or attention, right? Essentially, some types of awareness or attention can be captured through the omega, right? Because essentially, for instance, you can a little bit do tricks with omega. So this is where random utility apparatus or the modeling that is a monster, right? Can do a lot of things. Is hitting its limits. Because attention, is a very binary thing. So when you are not aware of something, you do not choose it, right? So a way to trick the model to be able to capture the situation is by creating a mood in omega such that the alternatives that you're not paying attention are ranked at the very end, such that you never choose it, right? But it's a trick. It's basically you are hacking the random utility model. Random utility model is not designed to capture awareness because, as you can see from my description of the model, it just maps any omega to a utility. So it still requires that you rank everything, right, in the choices, and you are aware of everything. So the way to hack it to introduce attention is by creating an omega that sends the things that you do not pay attention to the very end of the ranking. So are the things that are the worst according to that utility connected to the omega. But that's a hack of the model, right? So as you can see, even random utility model has limitations, right? Because it does not capture the inattention, right? It's not that magically creating an omega is now making the fact that you don't pick certain alternatives, right? You can only map the omega to a utility. So the only kind of heterogeneity that you can capture with the random utility is just variation in rankings. So each omega maps to a different utility, hence a different ranking. So the only types of things we have described, for instance, is variation in risk aversion, just changes how you rank lotteries, right? Variation in the taste of Cobb-Douglas just change how you rank alternatives. Variation in the states of the world changes how you rank cold versus hot drinks, right? But only is a change in ranking. So that's the limitation of random utility. Omega can only be transformed into a ranking, right? In the end, it's going to be mapped to a ranking. So as long as you can take combination of rankings and describe behavior with that, this is random utility compatible, right? Attention is something that is a little bit beyond that. So you can only do it by a hack, okay?
Okay.
But that's a great question. That's a great question, okay? Great, so now, what is the random utility model in full generality? So Rho has a random utility representation, RU. If there exists a random utility, so hence a distribution of utilities over omega, and of course, a probability of A of any given item X is equal to the probability, of course, over this event C of XA. So expanding it, you can just take the probability of omegas in capital omega such that the utility of X is greater than Y for all Y, okay? And of course, here there is a typo, sorry about that. Okay, great. So do you understand? So this is it, right? So essentially you're measuring, right? All the events, omega, states of the world, moods, variation in taste, where X happens to be the top, right? And that's now what you're predicting. So this is of course a much saner prediction in my view, Whereas if I'm trying to predict what you like, what you're going to choose, I can only predict the probability that you're going to buy Subway versus Tim Hortons, right? I cannot possibly imagine that I can predict that you're going to choose Subway versus Tim Hortons, right? So if I'm asking, what Martin is going to do, I cannot do it, in good faith. I have no idea. But if I have enough information about Martin, from previous choices, I am confident that I can predict the probability that he's going to choose, Subway versus Tim Hortons, right? And essentially, you can see that this is something people do right now. So a lot of you, depending on how open you are with your data, may notice that Facebook, or Amazon, they start learning what you like, right? So the probability of choice of something, right? And essentially, that's why Amazon and other places are actually earning a lot of money, in particular Amazon, because they leverage, economists, decision scientists, and engineers, right, to try to predict what people like. And essentially, they are not predicting exactly what you're going to do. That's impossible. They're trying to predict they just have access to the probability of choice, right? Conditional on previous behavior, conditional on attributes, right? And of course, that's what they do, right? If they change the price of something, they know that the probability is going to increase, right? If they reduce the price of something, they know the probability is going to increase. And of course, our job is not just to say it's going to increase, which is the lazy way. It's actually telling us how much, right? And so now they can predict exactly what's going to be the discount that they need for you to buy something, right? But this is the object we're trying to do. So now,
in that sense, will you say that the difference in the example that you mentioned before for neuroscience, that the difference between econ and neuroscience is the focus on aggregate versus individual behavior with respect to this question in particular?
Yeah, so the focus on, as I would say, right? So is that we really need to be careful about what is the object of prediction that as social scientists we should focus on. So I think originally, right, we got a little bit lost as economists, thinking that we can predict individual behavior, right? And actually, we needed to predict individual behavior in order to construct a good prediction of the economy, which is the idea of the micro foundations, right? I think in essence, right, something that we have realized as now we have data is that the only thing that is predictable is the population share or the probability of choice. And it's the simple fact that a lot of people are really hard to predict deterministically. So we are not, deterministic objects that I'm gonna know, given your current state of the world, what is gonna be your next choice with probability 1. That's impossible, right? So even talking about a simple choice such as, buying from a restaurant, right? We realize, making introspection, and we can also have data about it, that people are changing their preferences, right? So preference stability, which is the basis of the traditional way of understanding human behavior, the chapter 3 Mascolet, this is not really a reasonable assumption and is not supported empirically. People often violate work, right? So what is the alternative to this? So the alternative I'm proposing to you, which is very successful empirically, is random utility. And essentially, this is saying, instead of predicting exactly what you're going to do, let me just predict the probability that you're going to do something, right? And I can no longer, focus on the individual, but I have to focus on a population of agents, right? And that's, of course, what Amazon does. They use, of course, your individual data, but they also pull it. So they have a collection, a population of individuals, and they study these patterns, and they condition, of course, on age, education, all the information they have to be able to make it a final prediction. But in the end, it's a population prediction, okay? So now, one important thing to do before closing this chapter is that this section of the chapter is a long chapter, is that another way to describe the distribution of random utility is by means of mu. Mu is the distribution of the random utility U. So random utility, you can describe it directly through the random object, right? Or by means of the distribution. And the distribution here is written using mu, is the probability of X in capital menu A is equal to mu of random U, conditional that the mu of A is greater than mu of B for all B in A. So this is an alternative distribution where I'm now thinking of mu as a random object, right? And there is a distribution here. Okay, now with this in hand, I'm going to stop because next class I'm going to do the random expected utility. So we're gonna take all these utilities for each mood, and instead of requiring it to be any utility, I'm gonna require them to be expected utility. So we're gonna study what happens when I do that. And essentially, we're gonna go and study this expected utility model. And at the end of the next chapter, we're gonna study what are the analogs of the generalized axiom of revealed preference, or the Afriad's theorem for random utility, okay? And then with this in hand, we're gonna conclude this random utility chapter, right? So essentially, this chapter was a little bit more motivational, and then we introduced the model. We studied this very classical logic model and the characterization of logic model. We discovered the IIA. IIA show us that logic is not great, right? So we're forced to move to more general versions of random utility. So now I introduce the more general model. So in order to see what other kinds of models can we study within this more general framework, I'm going to introduce the random expected utility model, where heterogeneity comes through heterogeneity in risk aversion, for instance. And once we have done it, we're going to introduce finally the Afriad's theorem for random utility. So as you can see, this is a little bit of an analogy, step by step, of everything we have studied, but introducing randomness, right? And this is the modern way decision theories study behavior, right? So in a way, it's an update of all the things we have studied, right? So everything we have studied still is useful, but with this twist of adding randomness to it, okay? So that's a little bit the spirit of this, okay? Yeah, Martin?
Yeah, one question. So we are not, when we are saying that AAA is a very restrictive assumption, so it is not, so using logic is very restrictive as well. We are not like rejecting the model we started talking about today for random conditional indirect utility, but only the logic model, right?
Yes, you're right. So the only model we have discussed that is not a great model is this parametric version of the model, right? Which is the logic, assuming these particular shocks that are additive, as Juan mentioned. So additive heterogeneity with average, mean, common utility, and also assuming that the epsilon on top of being additive is coming from this type 1 extreme value distribution, right? Without correlation, so the simplest possible model. This logic model that was great because it didn't require a computer to be actually implemented, and was adopted from psychology, is a great model to start, right? The study of this, but it's not a good modern way of describing behavior. And we were able to see this by studying the IIA. And the IIA, is a really bad assumption and shows the limitations of this model. So since that, now we're generalizing the model, right? We're studying what is called the general random utility model, which is way more general than logic, right? And this model is going to be the center of our study, right? And then as an illustration of what other things can I do besides logic, we're going to introduce this random expected utility, where the moods are going to map to expected utility model, right? So in particular, we're going to be able to study, variation in versus in risk aversion, which is impossible to do with the logic, right? So yeah, this is gonna be for the next class. So right now I'm gonna stop recording.